Okay, thank you, Nicolas, for the introduction. My name is Ruben Snellings, and I have met many of you already in some of the RILEM activities and during the conferences I've been to through the years. And also I would like to thank the jury, RILEM, for awarding me the medal and giving me the opportunity to present here for you the work I have been doing together with many other colleagues I met along the way that were very passionate about science. And as well as Susan has mentioned, to me as well, science is very much of a collaborative effort. And working with very passionate people has been very motivating all along the way. So I would like to thank them especially for that as well. So I have been working, I'm working now at VITO, the Flemish Institute of Technological Research. And I'm working in a group that's focusing on how to make the best use of residues of waste streams. And we're trying to extract most value out of these waste streams as possible. One way of making value of waste is also by using them in construction materials. And this is very much related to the topic of supplementary cementitious materials. And over the years, over the 10 years that I've been active in the field, supplementary cementitious materials or precursors for any other cementitious materials have been really within the focus of the research. So this is the presentation that will go over 3 different topics related to these SCMs, which is on contributions made to better assessing and better understanding the SCMs, and using all this knowledge to be able to unlock more SCMs for the future, because this will be the main challenge for the future, actually. I would also like to thank the organization for hosting us here and making this possible. I find it a very inspiring city, and on Sunday morning, when we had a little bit of time, we actually had the opportunity of visiting some of the landmarks here in Copenhagen. Here we have the Øresund Bridge. I'm not sure if I pronounce well. We went to the New Haven in Copenhagen, and of course, well, okay, you can see that I'm not a professional photographer. We also visit the Little Mermaid. But I also wanted to actually attract your attention not to the main, very well-known landmarks, but also to what I think are very inspirational features of Denmark. One of which is the clean energy you can see everywhere. You see the wind farms around. The other thing is, and the attraction to that has been actually, well, focused during the City Hall reception, is the clean water. People swim in the city, so that's also quite surprising to me. And the other thing is this big building, so that will figure on many of the pictures you would take from the Little Mermaid as well. And this building in the back is actually one of the biggest waste incineration facilities in Europe. It's being built right now. And it's so big that I don't know how high the tallest mountain in Denmark is, but they're building a skiing slope on it. So it's also one of the ways in which I think Denmark can actually inspire people to become more sustainable. And we need this inspiration because I think the challenge is quite formidable for the future. At least the challenge that for instance, the European Commission is addressing to us is that by 2050, industry has to cut its CO2 emissions by between 83 and 87%. To my knowledge, for cement industry, we cannot make these numbers as yet. So we need new ideas, and we need much more research, much more work being done before we can actually hope to even match this challenge. As you all know, if we don't do anything and others progress, for instance, in the field of energy, as you have seen wind farms becoming more cost efficient, solar power becoming more efficient, then actually, if we don't take any actions, then in the cement world, in construction, then actually our contribution to the CO2 emissions might actually go up to 25% by 2050. So I have been lucky enough to be able, in my work, to take a step back and look to this formidable challenge from, let's say, an analytical point of view, where we could actually simplify the work in model systems. So also that opportunity gives opportunities to actually better understand systems and assess systems. So the first part of the presentation will be about better understanding the SCMs. This is a figure I made to actually have an idea about, okay, if we need to meet the challenge, do we have enough materials there to reduce the amount of cement that we use each year? Well, this is a figure that shows that most of the blast furnace slag, for instance, 330 megatons per year is being used, but there's only a small amount that is not being used in cements already. So if you want to make further progress, we need to actually go and look to other materials and see where we can use more materials. Other materials like in fly ashes from coal combustion, or perhaps also the primary source SCMs like limestone, natural pozzolans, and activated clays, where we have still large reserves and we could make progress in reducing, for instance, CO2 emissions, but other environmental impacts as well. And it also could pay off to look at other residues. Susan also mentioned a few of those. And well, we have challenges there as well. They can be very heterogeneous, they can contain some contaminants, and we need to resolve these challenges by one way or the other, maybe by beneficiation treatments, by pre-treatments, by activation, by finding new systems, adding smart additives, and so on and so forth. Okay, so in the presentation I will showcase some of the work we have done lately. And one of the, I think, nicest contributions was to progress work by SCM EDX analysis. I was so lucky to be able to contribute to that, but much of this has been developed with my colleagues at EPFL. As SCMs can be very complex materials, this is a picture, for instance, of calcareous fly ash, where you can see this is a normal BSC picture here. And this is the same picture, but with the element mappings of silicon, aluminum, and calcium superimposed. So calcium is blue, silicon is green, and aluminum is the reddish color. And you can really see there's a very different populations in composition of particles. And better understanding what your material is composed of also can help you explain how they actually behave in cement. So you can analyze these pictures and you can define populations, and then you can also add them to cement and try to follow them during the hydration. And this proved to be very interesting because actually you can then see, okay, which of the components is most reactive, which of the components gives most contribution to the strength development. And we see, for instance, that here the blue components that you can see here were by far much the most reactive. And having much more of these, for instance, in your calcareous fly ashes would give you much higher early strength, much better reactivity. Another development was actually also in the field of X-ray diffraction. And as been mentioned before, conventional X-ray XRD analysis makes it not possible to distinguish between different kind of amorphous materials. And there is a new analysis method out there, and we tried it for instance, anhydrous systems, and we're also developing it now for hydrating systems, in which you can actually separate contributions, for instance, of slag and metakaolin in a blended cement, and this works pretty well. For instance, here, this is for anhydrous mixes. You can actually have a quite good correlation between what you measure and between what you weigh out. So also here, we think that there is considerable progress possible in assessing and characterizing these materials and also knowing how they react. Of course, both of these developments can be done only in research labs. So if we want to go to maybe more reliable test methods that can also be applicable in the field or at cement plants or for quality control, then we would need to have some simpler methods, but that are also as reliable in, for instance, predicting the compressive strength development. For this purpose, there are already quite a few promising test methods around, and we also did some work at EPFL, this work for kaolintic clays, in which we measured the heat flow as a function of time and we compared it to the relative strength of mortar bars. And we see that if we mix the metakaolin or the kaolitic clays in a system with lime, alkali, sulfate, and water, the heat flow that is coming out, or even the other properties like bound water or portlandite content, can actually be related to the standard mortar relative compressive strength. This work will actually be at the core of one of the new technical committees, the one on reactivity of supplementary cementitious materials. And the scope of this new technical committee will really be on the evaluation of the most promising new methods across a wide range of these SCMs, and to compare these to the existing reactivity test methods that are already out there and that give not always good results in terms of predicting strength. So what we really want to do there is to try and get to a pre-standard for reactivity testing, to develop a new kind of method that can help predicting the strength development. So the work is on the way there, and we hope to be able in 4 years to give you some encouraging results. We don't know, but we hope that we will get there. Okay, maybe now a bit more about taking a step back and looking into model systems. Well, as we see SCMs, then they actually react through the solution and produce, okay, calcium silicate hydrates and typical reaction products in combination with cements. The reactivity or the dissolution rate of these materials are known to depend on the composition of the SCM, for instance, the structure of the glasses, the basicity of the glass, the presence of hydraulic crystalline phases as well, and also the pore solution composition. Especially this latter part has not always been very much addressed when we are working in blended cement systems, for instance. So for now, I will show some results on how composition, pH, and inhibitors may actually affect the dissolution rates of your SCM. To take a step back, we simplified the system. So instead of looking at very heterogeneous SCMs, we synthesized glasses in the calcium, silicon, aluminum system. And they were chosen to compare well to, for instance, blast furnace slags, to fly ash, to natural podzolans, up to a silica fume. So to remember, the lowest one, the G1, is the most calcium-rich one, and the G6 is the most silica-rich one. So we synthesized these glasses in a lab furnace, and these are the XRDs, so they are quite homogeneous. We ground them, and we have these small pieces. They are actually a bit larger than what you would actually use in blended cements, but this is actually to do our dissolution experiments in very dilute solutions afterwards in a better way, so we can follow the buildup of ions in the solution over a longer period without having any precipitation of hydrates. So how does it work? Well, we did some batch dissolution experiments. So we added the glasses into a large volume of water. We fixed the pH to 13, and then we added, for instance, aluminum, calcium, silicon, to see what the impact of these ions in solution would be on the dissolution rate. So how do we calculate the dissolution rate here? Well, it's using this kind of formula. And here you have then the slopes, the buildup of, for instance, silicon in the solution here. And then you actually take the slope, and this is a measure for your dissolution rate. You want to do this over a limited time period, because at some point, when the concentrations go up, you will reach a hydrate solubility product and you will get precipitation, so you don't want to end up in there. So if you really want to see only the solution, you have to stay within this time period. If we calculate these dissolution rates and we then compare them, so these are the calculated dissolution rates here on a log scale, and then we compare them to the chemical composition. This means actually the glass structure as well behind. Then we can see a clear correlation between the calcium content for very typically blast furnace slag type of glasses. We see very high dissolution rates or higher dissolution rates, and almost an order of magnitude lower, we see the dissolution rates for silica-rich glasses. What you already need to see here is that, this is normalized by specific surface area. This, for instance, does not mean that silica fume, which is plotting around here, or would plot around there, is less reactive as a material than a slag, but silica fume is also an order of magnitude finer, has much more specific surface area. So would move up here if you would not do the normalization by the specific surface area. So where is this coming from, this dependence on, for instance, the calcium to aluminum plus silicon ratio? This is a picture of a glass structure here, and you can see that when you enter more of these sodium or potassium ions in the structure, you break up bonds between the silica tetrahedra, the silica and aluminum tetrahedra here. And the more depolymerized the structure is, the more liable to dissolution it will be. So this is something we clearly found for these model systems, but you can also find this when you look at, for instance, these systems that we were characterizing in the calcareous fly ash, and we were following it through SCM analysis. Also here you see, okay, this is a different measure here. This is the non-bridging oxygen over the tetrahedral oxygens. So this is this kind of formula, but it's basically doing the same as here. And you can see there's a correlation as well, very nicely. Apart from just looking at the glass composition, one can also look at the pH of the solution as one of the factors that actually determines the rate of dissolution. So herefore, we did some very simple experiments in which we took the glasses we made before, and we put them in this kind of a pipette with some, and we added a fixed amount of HCl or NaOH, and this is called a pH titration experiment. We were shaking the solutions for some time, and then we actually looked at for 30 minutes, and then we were looking at what the outcoming solution pH was and what the composition was of the cations in the solution. Based on what comes out, you can actually calculate, or you can see what the glass dissolution was during these first 30 minutes. This is for the most calcium-rich glass, and you see, okay, there is a clear dependence on pH. This is a very typical U-shaped behavior, so the higher the pH becomes on one end, you get more dissolution, and of course, when you go to very low pH, which you would never have in cement systems, of course, typical cement systems, then you get also much higher dissolution there. So also there we see this clear dependence on the composition of the solution, of the glasses. So we see here that when we move to more aluminosilicate-rich glasses, we really slow down the dissolution rates, and we get a very broad pH range where we get the stability of the glass. So for these glasses, you really need higher pH to be able to make them dissolve or react at the longer term. And this is what you can see also for the other glasses here. So these are very silica-rich glasses. They really become only soluble here at the higher pH range. One can calculate this from pH, but you can also look at the calcium, aluminum, silicon concentrations in the solution. And based on, okay, the difference between how much calcium you release and how much calcium is in the glass compared to how much silicon you release from the glass, you can also start calculating the leached layer thickness. So if there is a silica-rich layer at the surface of the glass or not. And one can really see that, okay, if you calculate equivalent dissolved layer thicknesses here, that they are similar at high pH, but there is really a big difference here at lower pH. So this is really indicative for calcium leached layers established at lower pH, actually of incongruent dissolution at lower pH. This has also been shown here. So here you see then the calculation of the leached layer thickness with pH as well. So what we suspect is, at least for calcium, aluminum, and silicon, there is congruent dissolution at higher pH, but incongruent dissolution at lower pH. Taking these results, one can actually come forward with this kind of dissolution mechanism. So at low pH and high pH, we start here at time 0. And at low pH, we establish this kind of leached layer. Okay. And then at higher pH, instead of having the leached layer acting as a protective layer because it becomes richer in silica, we actually have a hydrate layer being established there, so we get ongoing dissolution at longer terms. So this also explains why at high pH one can establish a system where we have hydrate formation and we have ongoing dissolution, while at low pH sometimes we have the complete stop of our reactions. So there's this positive feedback between the solution and precipitation, which goes through the solution composition. And this is very much something we often see, that pH or the presence of calcium in the solution can actually explain why a certain material behaves as hydraulic or pozzolanic, why it reacts at the longer term or not. One can actually also look at, okay, what if we put it in a broader picture, like what are the dissolution rates here, and what is then here the calcium to aluminum plus silicon, a molar ratio. And then these data here above are from Nicolo, for instance, from dissolution experiments, and here these are the data I showed you before. And one can actually distinguish 3 different regimes as well. So at very low dissolution rates, where we have little calcium, we have typically pozzolanic materials. Then moving up towards higher dissolution rates, we first encountered typically latent hydraulic materials, like this was the slag kind of glass. And then up there we have the hydraulic materials, like C2S and C3S, that have high dissolution rates. And also, of course, they have enough calcium to be able to precipitate hydrates and keep, for instance, aluminum and silicon in the solution lower. So you have this coupling between what hydrates you form, what sets the concentrations in solution, the pH, the calcium, the aluminum concentrations, the silicon concentrations in solution, and their behavior in blended cements. So finally, in also looking at what factors really can affect the SCM reactivity, one can also look at aluminum. And we actually really see that aluminum solution slows down the dissolution of the SCMs, especially for silica-rich SCMs. So for the G6, G4 type glasses, we see that when we increase the amount of aluminum here in the solution, we really decrease by, in this case, even more than an order of magnitude, the dissolution rate. And this has been shown before in many other publications as well, that you can actually have aluminum from the solution attaching to the surface of the glass and making passivating or stronger bonds that actually are much more difficult to disintegrate by the hydroxyl solution. So you get really this rate decrease by aluminum. And so now one can think, okay, how can we use these kind of insights in practice? And then maybe one has to think also, okay, what kind of aluminum concentrations do we expect in typical cements? For instance, in combination with cements, here we see if we start with this kind of a composition here, we have C3S, C2S, C3A, and so on and so forth. During early hydration, we mainly precipitate ettringite, and we have still some gypsum. Then we can get very, very low aluminum concentrations. At later hydration, on the contrary, when lots of our materials have reacted, as can be seen here, then we have, for instance, AFM, monosulfo, as the main hydrate, and then actually aluminum concentrations based on the solubility products and the other cations in the solution might be much higher. Similarly, for instance, if we would add calcite, then we do not have monosulfate, but ettringite and monocarbonate, so we could actually lower a little bit the aluminum concentrations. Whether this then leads really to an increase of the dissolution rates of typical SCMs, we don't know yet. It's very hard to measure aluminum concentrations, but it might be one way of getting more reactivity out of your SCM. So it's a possible route for improvement as well, or possible way to explain why these ternary systems containing calcium carbonate are so effective. So putting these results we've seen before on and comparing it to, well, concentrations you would expect when you have, for instance, ettringite plus gypsum still present, or ettringite and monocarbonate when we have calcite in the system, or ettringite and monosulfate alone, or others, or other aluminum hydrates that actually could determine the aluminum concentrations. One could actually expect that, for instance, in systems where we add calcite, we can enhance the dissolution and enhance the reactivity of some SCMs. Okay, so I'm coming up to my conclusion now, and I would like to share with you some future perspectives on a world in transition. So to go back to one of my first slides, I wasn't aware that Copenhagen would already achieve carbon neutrality by 2025. But there's so many signs that actually it could, And also, like in Belgium, we see that, for instance, wind energy and solar energy is becoming so cheap that actually we also have to think that about a time when the typical SCMs we have been using will not be as easily available as they are now. For instance, coal, fly ashes from coal incineration, at least in Belgium, we don't have access anymore because they phased out coal combustion electricity. Instead, we might have different kind of materials, SCMs, that come up, or that we should be able to try and use as SCMs, or precursors for more environmentally friendly, like from the incineration facilities. And of course, there might be also other materials that are coming from dredging and so on and so forth that might be interesting as SCMs as well. So we need to be able to prepare for a change in society where we will have more recycling, less carbon-intensive technologies, and also other raw materials to make our cements more environmentally sustainable. One way of doing this, or several ways of doing this, or a general way of doing this, is by looking at beneficiation and pretreatment technologies and activation. Beneficiation, of course, then you want to change really the SCM or the precursor by any kind of technology, like going from classification, grinding, maturation, calcination and carbonation. And we will really need these kind of technologies that should be cost effective, of course, to be able to use much more of these other residues that are mostly being just landfilled as waste. We need beneficiation, but we also need smart activation. We need to optimize reaction environments. We need to take advantage of synergies between components, like adding the calcium carbonate might reduce aluminum concentrations, might actually then also induce more reactivity. And okay, we can look at other systems, alkali activation, we can look at other cements, and we hope that in a diverse future there will be much opportunity for researchers to actually find new solutions to our formidable challenge of becoming more sustainable. So with that, I would like to thank you for your attention. And I also would like to thank all these people here on the slide for putting up with me through all these years. People from KU Leuven, where I did my PhD, first on natural zeolites as a geologist, then people at the University of Ghent that give me the opportunity to work on completely recyclable concrete, the people at EPFL that allowed me to take a step back and work on model systems, and my colleagues now at VITO that challenge me with all kinds of new waste streams and residues to be used. Of course, I would like to thank the organization and RILEM again for awarding me the medal, and it is an honor, and I hope that I can continue more and show you more of this work in the future.
Thank you very much, Ruben, for this excellent lecture. We have time for a couple questions before I hand up the medals to the medalists. I guess I will. The presentations were good, so. Any question? Oh, yes. Karen?
Yes, okay, that's a good comment. But of course, I mean, this is a lot about also political lobbying, and as industry as a whole and as a society as a whole, if we need to reach the goals for 2050, we make a huge impact. So maybe we should even strive to do more than that. Yeah.
One last question.
Maybe I can ask a question. I was wondering, this research in model systems is of course very interesting, but how easy can you transfer it to the real systems? Or do you have to take intermediate steps? Or
well, working in model model systems is of course inspired by, okay, you're looking at systems that are very complex, as in showing in more in the characterization part, in assessing the SCMs, you can really see that some of these SCMs are very complex mineralogy. But at some point you need to take this step back and look at it in model systems, because you need to figure out which parameter is affecting what to what extent. So it's more like giving you guidelines and ideas than having a direct applicability. It's like, okay, we know that now aluminum also affects the dissolution rates. Then maybe we can test it and by changing the aluminum concentrations or using hydrate assemblages that have lower aluminum concentrations, maybe we can get more reactivity out of our SCMs. So it's more like, I think you have to use it in an indirect way than giving you direct indications of how you should do it.
Thank you once again, Ruben.